Okay, hi, good morning, everyone. So we're looking at the part two of the paper two. Okay, paper two, part two of our holiday homework. Okay, so this is the question. Let's get right into it, lah. Question number one, diagram 1.1 shows the arrangement of planets orbiting the sun. So this is a very normal picture. Complete the sentence below. So Kepler's first law is the law of orbits. Okay, so it's either the orbits of each planet are a circle. Definitely, if you see the word circle, it is not correct, lah. Okay, so this is the one that is correct. Okay, every planet moves along an ellipse with the sun located at actually one of the focus. Okay, one of the focus of the ellipse. Actually, the one in Malay is more correct lah. Okay, satu daripada fokusnya. So an ellipse always has two focal points, which makes it an ellipse lah. Okay, so on diagram 1.2, draw the lines of the minor axis and the major axis. So the minor axis is this. Okay, and then the major axis is one that cuts across like this. Okay, this is the major axis. Okay, and then mark and label the focal point. Okay, so there are actually two focal points. So usually what I will tend to do is I will tend to take, okay, from from this point in the center, okay, from the point in the center over here, usually I will take a halfway point, and then the other one is the halfway point. Okay, and I will label these two as my focal point. Okay, next, what will happen to the motion of the Earth when it is the farthest point from the sun? Okay, so this one is law of areas lah. Okay, so when it is further from the sun, that means if the planet is if let's say this is the sun, okay, and then the planet is here, we know that the further it is away from the sun, the gravitational pull is further, so it will move slower lah. Okay, so the motion will be, it will orbit at a lower speed. Okay, lower speed or lower velocity lah. Okay, actually lower linear speed lah, but fine, lower speed is also fine lah. Okay, the point is this, the further you are away from the sun, okay, you move slower. Okay, but you cover a same amount of area as when you're nearer to the sun. When you're nearer to the sun, you will orbit a lot faster. That's why you cover a longer piece, but the area is still the same. Okay, that's the law of areas lah. Okay, Kepler's second law. Okay, diagram 2 shows a slinky used to demonstrate how a longitudinal wave is generated. Okay, so what is the meaning of a longitudinal wave? So longitudinal wave is the wave where the direction of wave propagation okay, is parallel. Okay, and I'm going to align this word, okay, to the direction of vibration of medium. Okay, the medium can be a spring, can be a water wave or whatever lah. But suffice to say, okay, that this is the only word that differentiates between a longitudinal wave and a transverse wave. Okay, the rest of the words is the same. Direction of wave propagation and direction of vibration of medium maintain. Okay, so if it is a transverse wave, then the word parallel you just change to perpendicular. That's it. Okay, so it's a very easy definition to try to remember. Okay, the only two different words are parallel and perpendicular. Okay, on diagram 2, mark with arrows the direction of the hand movement to generate a longitudinal wave. Okay, so first of all, I want you to notice that there is the word arrows. Okay, so it can be two arrows or one arrows, but we know that in order to generate a longitudinal wave, the hand has to go back and forth. So when you draw the arrows, okay, you can either choose to draw two different arrows like this, or you can draw one like this, but it must show both directions. Okay, the most important thing is that it must be both back and forth lah. Okay, so depan belakang, not just one way only. Okay, and please take note of this kind of, all these kind of small technical things lah. Okay, you need to be aware of. Okay, the transverse wave in diagram 2, it's not even the transverse, it is a longitudinal wave. It's okay. It's generated at the frequency of 5 Hertz. So what is the time taken for particle to travel from point X to point Y? Okay, now point X to point Y are what we call coherent points. So they are at the same phase. So which means that you're talking about one period, one wavelength. So the time taken is actually, so this question is actually asking for the period, but it is asking in such a way that you need to understand that the period is from one point to the next point, but it is at the same phase. Okay, this is in the middle of rarefaction over here, and this is in the middle of the other rarefaction. Okay, so we're talking about calculating the period. Okay, and so if you remember the relationship between period and frequency, period is equals to 1 over frequency. Okay, and so this will be 1 over 5, which will be 0.2 seconds. Okay, the speed of the wave in the spring is kept constant. So what must be done to double the wavelength of this wave? Okay, so let's think about this. Wavelength equation is V equals to F lambda. Okay, and so this is the speed. You want to double the wavelength. So let me reverse this. V equals to V over F equals to lambda. If you want to double the wavelength, since this is kept constant, okay, therefore the thing that you have to change is the frequency lah. Okay, so since you want to double the wavelength, the frequency has to be lessened by half. Okay, so you will have to vibrate at a lower frequency. Okay, or frequency is lowered by half. Also can lah. Okay. Okay, let's proceed to question number 3. So diagram 3 shows a bar magnet that is being pushed towards a solenoid. Okay, and notice that it's already inside and it continue to push in. So this is a slightly different situation than what we're used to. Okay, so what is meant by electromagnetic induction? So electromagnetic induction is the production, okay, of an induced EMF by the cutting, okay, of magnetic flux. Okay, production of induced EMF. I guess if we say induced current, so it wouldn't really be such a wrong thing lah. But technically, we're talking about induced EMF because that's the one that induces the current. Okay, state the polarity at P when the magnet is moved towards the solenoid. Okay, now right now, look at the position of P here. The one that is approaching is the south pole. So P will also turn into the south pole. Okay, because it wants to still reject the pushing in of the S pole. Okay, so when the magnet is pushed towards the solenoid, mark the direction of the induced current and show the direction of the pointer of the zero. So if you use your right hand grip rule, okay, so the right hand grip rule, the thumb always points towards the north. So if here is south, if here is south, here will be north lah. Okay, so when you point it this way, you will find that facing you is all going downwards. Okay, so these are all going downwards like this. Okay, so therefore, if this one follows here, this will be going downwards here, 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 and all this will be also going downwards. Okay, therefore, the direction of the pointer of the zero-centered galvanometer, remember, galvanometer originally starts at 0. Okay, and the further you are away from 0, the bigger the current lah. But right now, what we want to know is where is the galvanometer going to point? So galvanometer points towards the direction where the current is coming from. So it will be deflected to the left. Okay, always points towards the direction where the current is coming from. Since it's coming from the left, it will be deflected towards the left. Okay, and again, remember this: the further you are away from 0, which is the center, okay, the bigger the current is. Okay, so don't be fooled by this one. Okay, state one method to increase the induced current. Now, there are many methods, okay, according to Faraday's law. So one will be to increase the number of turns, okay, on the solenoid. This is the normal one lah. Okay, or to increase the strength of the permanent magnet. Okay, or finally, which is usually the one, is to increase the speed of the magnet lah. Okay, increase the speed of the, oh no, no space, the magnet's motion. Means you push in faster, you push in slower, push in faster lah, or you pull out faster. Okay, either one. So name the physics law in determining the induction current direction. Okay, induction current direction is Lenz's law. Okay, Lenz's law, again, be aware of the spelling, L-E-N-Z. Okay, of course, the most important thing is to differentiate between Faraday's law and Lenz's law. Faraday's law is how to make the current bigger. Okay, it is directly proportional to blah, 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 blah. Lenz's law is how to determine the direction of the current. Okay, in a gist lah, okay, the actual law is a very wordy, this one. Okay, but basically Faraday's law is how to make the current bigger, and Lenz's law is how to determine the direction of the current. That's what we use. That's what we use these two laws for. Right. Question number 4. Diagram 4 shows the transistor circuit to be used as an automatic switch. This is a downward transistor, so the type of transistor will be an NPN transistor. Okay. State the function of this one. Now, in our previous video, we talked about this. The purpose of that particular resistor is to control the base current. Okay, you control the base current so that the transistor will be taken care of, because the transistor cannot have too big of a current, otherwise it will spoil. Okay, so state one characteristic of component Y. Okay, component Y is an LDR. Okay, so it's a light dependent resistor. So it will have it has high resistance. Okay, when it is dark. Okay, when it is dark, it will have high resistance lah. When it is daytime, it will have smaller resistance. Okay, now the bulb in circuit lights up at night. So in diagram, mark the direction of the current flow. Okay, so now let me rub all this off. Okay, the direction of the current flow, of course, there will have to be current flow from here to here. Okay, all the way lah. Okay, it will flow this way. So it's like 3 loops. Okay, all together. Basically, this one has to flow this way, and this one has to flow this way. Okay, that's all we want to know. The base current has to flow, and then of course the collector current flows because the emitter current also is flowing. Now the transistor will be switched on when the base voltage is 1.5 volts. Okay, so you need to have a base voltage of 1.5 volts over here. Okay, now if the resistance of X is 10.5 kilo ohms, so this one is given as 10.5 kilo ohms. Okay, calculate the minimum resistance of Y. Now, when you look at this, of course, our first impression should be whenever we're given a resistance of one and then the voltage of the other, and you're given actually 4 batteries over here. This is a hidden information that is not clearly given to you. Okay, we have to assume that every battery is 1.5 volts. That's the standard one. So if every battery is 1.5 volts, 4 batteries, which is shown in this picture over here, will be 6 volts. So here we are talking about the voltage divider circuit. Okay, now if this is 1.5 volts, you know that this one has to be 4.5 volts already. Okay, because of the voltage divider. So you want to know what is the resistance over here lah. Okay, so there are many ways you can calculate this, and I guess the easiest way would be to use the 1.5 as our this one lah. Okay, so we know that the resistance of RB is what we want to count. This is the resistance that we want to count. Okay, so I'm going to call this RB lah. RB over RB plus the total lah. Okay, 10.5. 10.5 equals to 1.5 volts over the total voltage is 6 volts. Okay, this is one possible way to do this. If you don't want, if you feel that it's easier to use the other one, this would be the 10.5 over RB plus 10.5 equals to 4.5 over 6. Either one of these is fine. Okay, the most important thing is that it must tally. The resistance must tally with the voltage. Okay, the resistance that you want to calculate must tally with the voltage that is provided there. At the bottom, it never changes. At the bottom, it must always be total resistance and total voltage. Total resistance and total voltage. Okay, so when you calculate this, either the left or the right way, it doesn't matter, you will still get the same answer where RB is equals to 3.5 kilo ohms. And the good news is you don't even have to change the kilo ohms to times 10 to the power of 3. Okay, just leave it as kilo ohms. It's totally fine. Okay, you get RB equals to 3.5 kilo ohms, whether you use the left method or the right method. Okay, because this is what we call the voltage divider formula. Okay, so voltage divider is whatever resistance must equal to whatever voltage for whatever resistor lah. Okay, but at the bottom must always be the total resistance and total voltage. Okay, so learn to differentiate this lah. Okay, you can use this pair or you can use this pair, but this one and the total resistance never changes. Okay, all right. Explain why the bulb in the circuit lights up at night. Okay, so this is an explanation question. Okay, and since it is 2 marks, so of course, first of all, we know that the LDR, the resistance increases at night. Okay, so at night, resistance of LDR increases. Okay, so because of that, because the resistance increases, therefore the voltage increases, base current flows. Okay, and actually, you know what? Let's not use voltage, so we should use potential difference now. Okay, because the potential difference will change. Okay, the potential difference increases. Okay, base current flows and the transistor is switched on. Okay, transistor switch on, therefore the LED will also switch on lah. Okay, so the most important thing is this. For your transistor to be switched on, usually if we work it backwards, it makes a lot more sense. We want the transistor to switch on because if the transistor is off, the bulb will be off. Okay, so how do you turn on the transistor? Base current must flow. How do you have base current flow? You need to have a bigger voltage at the bottom. Okay, at the bottom, which is over here. Okay, the base voltage must be big here so that your base current can flow. And how do you get a bigger base voltage? You need to have a bigger resistor. Okay, so bigger resistor means you will have a bigger base voltage. You have a bigger base voltage, you have current flow. You have current flow, you have transistor switch on. Okay, this order, if you remember it, even if you don't understand it, you can remember it. Okay, if you remember it backwards, actually, it's easier. Okay, what must you do for this to happen? What must you do for this to happen? Let me repeat. The most important thing is, at the end of the day, transistor must switch on. How does transistor switch on? Base current must flow. How does base current flow? You need to have a big potential difference at the base circuit. How do you get a big potential difference at the base circuit? You need to have a big resistor. And how do you have a big resistor? You use the LDR lah. Okay, you need to have a big enough resistance. It is not okay, it is not. If you did a calculation just now, it's 3.5 kilo ohms, right? Okay, so this is 3.5 kilo ohms, this is 10.5 kilo ohms. Okay, so what what you notice is that it is not the bottom resistor must be bigger than the top resistor. No, it is just that we change the resistance to make it bigger. Okay, so that the voltage will be much bigger. Okay, voltage much bigger, then after that you can have a big enough base current. That's all you're doing. You're just increasing the resistance of the base circuit. Okay, that's the key to this whole thing lah. Okay, increase the resistance of base circuit, and then you have everything flow. Okay, so it's a very important I feel like it's a very important explanation to remember. Well, partly because if you understand the flow, it becomes very easy lah. Okay, but of course remembering the flow is of course one battle in itself lah. Okay, let's continue on to question number 5. Diagram 5.1, 5.2 show the formation of a virtual image by two convex mirrors. Okay, two convex mirrors with different curvatures. Now, the position of objects from both mirrors is the same. Okay, so the object difference, from the mirror, okay, the object is different. The object is at the same place, except that you're using two different mirrors with two different focal lengths. So what is meant by the virtual image? A virtual image is an image that cannot, okay, be captured on a screen. Okay, and just as a reminder, a real image, okay, a real image is an image that can, okay, be captured on the screen. That's the difference between a real and a virtual image. Okay, so cannot be captured on the screen means you can put it on your hand, you can see it, okay, because it doesn't appear on the screen, it appears in front of you. But a real image is one where if you put a piece of paper or a screen, okay, you can see it on the screen. That's a real image. Okay, compare the height of the object. So the height of the object will be the same. Okay, compare the curvature of the mirrors. Okay, now this is a very, very important thing lah. Okay, now the curvature of the mirrors. If you look at how the mirror is curved, obviously one look and you can see lah. Okay, that 5.2 is more than 5.1. Okay, 5.2 is more curved compared to 5.1 because look at the bend. Okay, look at this bend, much less. Okay, compare the focal length. If you look at the focal length, you're looking at this distance over here. Okay, of course, 5.1 and 5.2 are 5.2 is smaller than 5.1. Okay, and then you compare the size of the image form. You're looking at this. Okay, 5.2 is also smaller than 5.1. Okay, it's a very simple comparison lah. So, state the relationship between the focal length and the curvature of the mirror. So, if you take a look at these two, focal length and the curvature of the mirror, since the sign is terbalik, so one bigger, one is smaller lah. Okay, so the bigger I'm going to use curvature of mirror. The bigger the curvature of the mirror, okay, the smaller the focal length. Okay, and then state the relationship between the focal length and the size of the image. So the focal length and the size of the image, since it is in the same direction, will be one bigger lah. Okay, so the bigger the focal length, the bigger the size of the image. Okay, what happens to the size of the image formed in diagram 5.1 when the object distance is increased? Okay, so this one, if you don't believe, you can always use a spoon lah. Take a spoon, the back side of the spoon, and you bring the spoon further. Okay, normal thing to do, the spoon will definitely show a much smaller image. Okay, so the size of the image will decrease. Okay, so state one application of the convex mirror that is used for security purpose. Okay, this is almost a giveaway question now. We call this a security mirror lah. Okay, security mirror, which you use, you know, at the store, or like if you go to 7-Eleven, you see the mirrors that is on top of the ceiling. Okay, that's a security mirror. Okay, I find this a very interesting question because it is almost a giveaway. Okay, because the answer is actually in the question, security and mirror. Okay, let's go to question 6. So diagram 6.1 shows water in a container. The water spurts out from a hole at point A due to pressure of the liquid. Okay, so you can see the difference over there. Now, what is meant by pressure? Pressure is force per unit area. Okay, this is standard definition. Now, compare the depths of water at point A and point B. Okay, remember, our depth is calculated from the surface of the water, not from the bottom. Okay, so we're talking about this depth and this depth. Okay, so obviously, B is more than A lah. Okay, the depth of water at point B is bigger than the depth of water at point A. Okay, then of course, the next thing is to compare the horizontal distances of X and Y. Okay, we are looking at this distance and this distance. So of course, X will be smaller than Y. Okay, X will be smaller than Y. So relate the horizontal distance to the depth of the water. So the bigger the depth, okay, the bigger the distance. Okay, I'm going to use short form lah, but please write in full sentence. Okay, then relate the depth of the water to the pressure of the water. Of course, the bigger the depth, okay, the bigger the pressure. Okay, just to remind you, everybody, that you know, if you notice in question number 3, they give you horizontal distance first and then the depth of the water. Okay, so you need to make sure that your relationship is written in such a way that it must make sense. The bigger the depth, the bigger the distance, because the depth determines the distance and not the other way around. Not the bigger the distance, the bigger the depth. Means that it is further means, oh, you know, it causes the depth to be bigger. No, okay, it's always the one affects the other. So be very careful when you write relationship. Okay, don't be fooled by the question. Okay, state another factor that affects the pressure in the liquid. Okay, formula for liquid pressure is P equals to rho Hg. Okay, so of course one is the depth of the liquid lah. Okay, so notice that the other two is actually the density and the gravitational acceleration. The more popular answer, of course, will be the density of the liquid. Okay, different liquids will have different density, The bigger the density, of course, you have a bigger pressure lah. Okay, a less popular answer, of course, will be the gravitational acceleration, especially if you are only conducting the experiment on Earth. Okay, or well, if it is a comparison between you know, the surface of the Earth and also on top of the hill, where the gravitational acceleration is slightly less, okay, also can. But I think, you know, honestly, if you ask me, both answers should be accepted lah. Okay, although the more popular answer definitely will be the density of the liquid. Okay, diagram 6.3 shows a water reservoir. Explain why the dam walls are made thicker at the base. Okay, and it's a 3-mark question, which I find it to be very interesting lah. Okay, so you tell why and then you explain it. So the reason why the walls are made thicker at the base is to withstand the bigger pressure at the base. Okay, sorry, the bigger liquid pressure lah. Okay, the bigger liquid pressure at the base. That's the reason why the walls are made thicker. Okay, and so then you have to explain how is it that the liquid pressure is bigger. Okay, so the base has a higher depth of water. Okay, so it has higher liquid pressure at base compared to if you're doing it at the surface of the water lah. Okay, of course, if you want to talk about, you know, the fact that there is atmospheric pressure on top of the liquid pressure, also can lah. Okay, but I feel that if it is 3 marks, please make sure that you have at least 3 points. Okay, just write whatever you want to write, whatever that you know is true. Okay, but I feel that the main point is the first one. Okay, the walls are made thicker because it needs to withstand a much bigger liquid pressure at the base. Okay, I think that would be the answer. Okay, diagram 7.1 shows air bubbles produced by an air pump in an aquarium filled with fresh water. Okay, so why does the volume of the air bubbles increase as it moves towards the surface? Okay, so as it moves towards the surface, this is a standard one. So at the bottom, the bubble will be small, and then as it moves towards the surface, it will get progressively bigger because the pressure. Okay, gas pressure in the bubbles decrease. Actually, not in the bubbles, I should be on the bubbles. Okay, and you know what? Yeah, let's not put the gas pressure. Let's just put pressure on the bubbles decrease. Okay, there's less pressure, so the bubble will expand in volume. Okay, and so the physics law involved here, since you're talking about the relationship between pressure and volume, okay, so this would be Boyle's law. Okay, take into consideration the spelling, B-O-Y-L-E. Okay, an air pump releases an air bubble with a volume of 5 at the depth of 0.5. Okay, calculate the air bubble when it reaches the surface of the water. Assuming now, if they give atmospheric pressure, you know that you will have to use atmospheric pressure. And since it is all in meters, so at the bottom here is 5 centimeter cube, and the pressure is 10 meters water plus another 0.5 meters of water. Okay, so P1, the formula is P1 V1 equals to P2 V2. Okay, this will be 10.5 because 10 plus 0.5, okay, then times with 5 centimeter cube. Okay, equals to P2. Now at the surface of the water, okay, at the surface of the water over here, only this is left, okay, which is 10 meters water lah. Okay, so 10 times V2, which is what you want to calculate. Okay, so you calculate this, you get V equals to V2 equals to 5.25 centimeter cube. Okay, which will give you the answer lah. So what is the change in the volume of air bubbles on the water surface when fresh water is replaced by seawater? Now, so the interesting thing is this. The question is, what is changed in the volume of the air bubbles on the water surface? Okay, in the question before, we just talked about how liquid pressure is, is affected by the density lah. So when people look at this question, you'll be like, oh, okay, freshwater, seawater, which is more dense? Seawater is more dense, correct. But look at the question. The question is on the water surface. On the water surface, whether you're in freshwater or in seawater, the water doesn't affect the pressure anymore because you're already on the surface. The only thing that is affected is the atmospheric pressure. So it will be unchanged. It is a trick question actually. Okay, it is designed to see whether you understand or not the words on the water surface. Because freshwater and seawater, everybody look at freshwater, seawater, then they will immediately think, oh, okay, freshwater is less dense than seawater. Yeah, lah, because seawater got more salt. Then, oh, less dense means you change to seawater means, oh, that means the pressure will be bigger lah, because the liquid pressure, the density is bigger ma. No, question is on the water surface. On the water surface, the liquid doesn't matter anymore. Okay, if you say at the bottom of the ocean, then different lah. If you change the water in the aquarium to seawater, then that's a different story. But at the water surface, everything is just atmospheric pressure. Okay, diagram 7.2 shows the air trapped in a flask heated to a quantity of heat. After 10 minutes, the stuff is turned off. Now, based on 7.2, the reading on the bottom gauge does not show an accurate reading. So what modifications need to be made to the apparatus to get an accurate reading? Give a reason. So there are two things that they want, which is the rubber tube, and the second one is the stirrer lah. Okay, so when I look at this, I was like, where is the stirrer? So I guess they want you to add a stirrer in. So I'm going to talk about the stirrer first. Okay, so add a stirrer or use a stirrer, okay, to stir this one. And the point of a stirrer is to ensure, okay, the heat is distributed to the flask evenly. Sorry, the heat is evenly distributed to the flask. Okay, the heat is evenly distributed to the flask. So you put a stirrer here. Okay, then you kacau, 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 so that whatever heat that is on the water will be distributed evenly into the flask. Okay, otherwise maybe just the bottom only will get the heat, and then the side over here not so much. So that's why you need to have a stirrer. Okay, if you take a look at the rubber tube, okay, the point of the rubber tube is, okay, so if you look at it, when you heat up this flask over here that has air, the air is going to get hot lah. Okay, the air gets hot and it will flow into the rubber tube and give you the reading for this one. But the problem is the tube is made of rubber, and rubber expands very easily lah. Okay, especially if the gas or the air is very hot. Okay, so I can think of two possible answers for this lah. Number one, you change the rubber tube to a glass tube. Okay, change to a glass tube. Okay, and the reason for this will be less expansion. Okay, less expansion when hot air flows. Glass will still expand. Okay, yes, definitely glass will expand, but it will expand less than volume. Okay, than the rubber tube. Okay, so that's one possible answer lah. Now, another possible answer that I found when I was doing some research is you change to a shorter rubber tube. Okay, you change to a shorter rubber tube, and actually the reason will be the same lah. There will be less expansion lah, because I noticed that in this picture the rubber tube is so unnecessarily long lah. Like, why is it put so far away? You just give the gas more chance to expand the rubber tube, which you don't want lah. You use a shorter rubber tube, so it's less expansion. You get a more accurate reading. Okay, so for the same reason, I think you can use either one of the modifications lah. Okay, either you change to a glass tube or you use a shorter rubber tube. I think it's fine either way. All right. Okay, let's continue to question number 8. Diagram 8.1 shows the structure of a hair dryer. Okay, name one suitable material to be used as a heating element in the hair dryer. So heating element, you need it to be very high resistance lah. Okay, so usually it's tungsten, okay, or nichrome. The two elements with highest resistance in your syllabus lah. Okay, so remember the reason why we use this is because it's high resistance, and resistance always causes heat. Okay, so what is the meaning of 240 volts, 1100 watts? Okay, so this one is a little bit of a no compromise lah. Okay, you cannot write the word power rating because that's what it is. Okay, they're asking for the meaning. So the meaning, I want you to kind of standardize this. Okay, 1100 joules, and I know I'm writing joules because I want it to be in joules of energy is dissipated per second. Okay, because the word energy per second refers to the power. Okay, so 1100 joules of energy per second, and the way I get the 1100 from is of course the 1100 watts over here lah. Okay, so take a look at this. 1100 joules of energy is dissipated per second when provided with 240 volts of voltage or potential difference. It doesn't matter to me lah. Okay, the 240 volts, of course, comes from this one, from this 240. Okay, so and this is a very popular question. If electricity comes out now, this is a very popular question. They will always ask you what is the meaning of 240 volts, let's say 240 volts and 2000 watts. Okay, so it is best to use this like energy dissipated per second. Okay, then you use the 1100, just change the unit to joules. Okay, when provided with 240 volts of voltage. Okay, calculate the current flowing in the main circuit. This one, since you're given the voltage and the power, okay, you use P equals to VI, the standard one. So power is 1100, voltage is 240. You calculate I, you get I equals to 4.583 amperes. Okay, now if the two fuses of 5A and 8A are available, ampere, which one is more suitable to be used in a hair dryer? Now again, the function of the fuse, okay, the fuse function the fuse function is to cut off the circuit, okay, when too much current overflows. Sorry, too much current flows. Okay, so the function is to cut off the circuit lah. Okay, so if you take a look at it, if we put it as 8 ampere, that means 7 ampere can flow, 6 ampere can still flow, you know. But the problem is we only need 4.583 amperes. We don't want too much, because if we have too much current flowing, then you will cause the perkakas, the electric equipment to rosak lah. Okay, so of course we want 5 ampere, which is the nearest to 4.5. We don't want 4 ampere. Okay, 4 ampere definitely cannot, because we need 4.583 amps. A minimum of 4.583 amps for the hair dryer to work correctly. So if we have a 4 ampere fuse, the moment the current hits 4 amps, it's going to cut off. Then it's like, oh, my hair dryer rose up. But the hull is the fuse, is you put in the wrong fuse. 5 is yes, 5 is higher than 4.583, but not too high. Okay, remember this 4.583 is the minimum current you need, okay, for it to function correctly, to function properly. A little bit more is not too bad. Too much more, like 7 amps is too much already. Okay, you will cause the hairdryer to roast up faster. Too small of a fuse, 4 amps, is not going to allow 4.583 ampere to flow in. Okay, so you don't want that lah. So 5 is just nice lah. Okay, 5, or if you can find a 4.6 amps, for 4.6 amps very hard lah. Most fuses are usually 1, 2, 3, 4. So very nice round numbers lah. Okay, so 5 amps is the best. Okay, diagram 8.2, 8.3 shows two different electric circuits for the fan and the hair dryer's heating element. Now, what happens to the fan in diagram 8.2 and 8.3 when switch B is turned off? So if you take a look at this, when switch B is turned off, the fans here still flows because there is already a complete circuit. Okay, actually, even the heating element also is still possible because switch B is like a useless switch over there. But in diagram 8.2, the switch B is a very important switch because it is connected to the fan. Okay, and so if switch B is turned off, okay, the fan doesn't turn on. And the color in 8.3, the fan turns on. Okay, so based on your answer in 8C1, suggest the more suitable circuit for the hairdryer. Give one reason. Well, obviously it would be 8.3 lah. Okay, because the fan can be turned on and can be controlled. Okay, because of switch A, and can be controlled. Okay, you can control it. You can turn on and off the fan if you want. Okay, Okay, let's go to question 9, everybody. So, of course, I need the space on the left over here, so you can just refer to the question. So 9.1 shows two identical metal balls heated for a few minutes in boiling water. The two metal balls are then transferred into two beakers containing liquid X, liquid Y. Okay, diagram 9.2, 9.3 show the initial and final readings of the thermometers in liquid X and liquid Y. Now, before we begin, I just want to mention that this is a very unconventional question 9 and 10, because 9 and 10, the comparing question is not supposed to be question 9 or 10, it's supposed to be question 11. Okay, but let's just answer it as if it's a normal question. Okay, but let's take a look at it. So what is meant by specific heat capacity? So specific heat capacity is the heat required to increase the temperature of, of 1 kilogram of substance or object, okay, by 1 degree Celsius. Okay, the most important thing, of course, when you're talking about this, is the words 1 kilogram and 1 degree. Okay, you're going to increase temperature lah. Okay, so you need to have these two units in there. Okay, so using diagram 9.2 and 9.3, compare the specific heat capacity, compare the final readings, and the change in temperature in liquid X and Y. Okay, so let's first talk about the specific capacity. So specific capacity, X is 2100, Y is 4200. So in terms of the specific heat capacity, X will be smaller than Y lah. Okay, of course, please answer in full sentence. Okay, don't just give my short form version. Okay, secondly, the final temperature. Okay, the final readings. So 40 is for X and then 30 is for Y. Okay, so the final readings. Okay, the final readings, X will be more than Y. And then the change in temperature. Okay, the change in the temperature, if you notice, this goes from 25 to 40. Yeah? So this is plus 15 degrees Celsius. Manakala, this is only plus 5 degrees Celsius. So obviously X has a bigger change than Y lah. Okay, X is more than Y. Now, state the relationship. Okay, state the relationship between the specific heat capacity and the change in temperature. Okay, so the first one is this one, specific capacity and change in temperature. Since they are both different signs, okay, so obviously one go up, one go down lah. So again, think about it. Which one affects which one? Obviously, the specific capacity affects the change in temperature. So the bigger the specific heat capacity, okay, the bigger the specific capacity, remember, is different direction. So the smaller the change in temperature. Okay, the smaller the change in temperature. And then finally, state the physical quantity. Okay, state the physical quantity measured by a thermometer. The physical quantity measured by a thermometer is the temperature. Okay, it's a very strange question to ask right at the end. Okay, fine. Now explain why a cooking pot's body is made of good heat conductor, whereas the handle is made of poor heat conductor. Okay, so since this is specific heat capacity, you need to talk about specific heat capacity. So it's a 4-mark question. Okay, so you need to have 2 marks allocated for the cooking pot body and 2 marks allocated for the handle. Okay, so the body of the cooking pot has a low specific heat capacity. Okay, and the point of it is it's a good heat conductor, so it has a low specific capacity. So this ensures the food gets cooked faster. Okay, since it is a good heat conductor. Then you talk about the handle. The handle is a poor heat conductor. Why? Because it has a big specific heat capacity. So the handle has a big specific heat capacity. And again, nothing to do with the food. What do we do with the handle? We have it a big specific capacity, so it takes a long time to heat up. Okay, so it takes a long time. Actually, we shouldn't say it takes a long time to heat up. We should say it's harder to increase in temperature. Let me see. It can absorb more heat, okay, without a raise in temperature. Okay, therefore, keeping the user safe from burning. Okay, so it keeps the user, whoever is holding the handle, it doesn't keeps it safe from this one. Actually, it can absorb more heat without a raise in temperature. Actually it's before rising in temperature. Okay, but I think the idea is there. Okay, so body of cooking pot has a low specific capacity. If you want to add on a little bit more to this, you can write it raises, temperature, okay, rises easily with a bit of heat. Okay, it means you just need to provide a little bit of heat, the temperature will rise already. Okay, 2100 and 4200 is a very big difference. Okay, in terms of this one. Okay, then after that, the next question. So diagram 9.4 shows frozen meat is put on a glass plate to defrost. So this is a glass plate. Okay, the time taken to defrost the meat is more than an hour. Table 9 shows the specifications of a defrost plate. Okay, so you have all these funny things over here: specific capacity, color of plate, surface area of plate, arrangement of plate. And then of course you have to make the best choice. Okay, when I was doing this, I did a little bit of research into this, and I thought that it was a very weird question to ask. Okay, because simply because I think that when I remember reading this once, that defrost plates are actually not very much different than if you put it in you just put it in the fridge, take the meat from the freezer to the fridge and let it defrost overnight. It's the same, and it's actually less dangerous in terms of bacteria. Okay, but anyway, asking this question. Okay, so here is the strange thing. We want the specific heat capacity to be high. Okay, we want the specific heat capacity of the plate to be high because we want it to be able to absorb as much heat without cooling down. Okay, we don't want it to cool down faster. So the problem with specific heat capacity is that if your specific heat capacity is low, it will get hot faster, okay, but it will also cool down faster, which is what we don't want for the plate. We want the plate to remain as hot as possible. Okay, so and if you think about it, the plate, okay, so this is how it will be. So let's say this is the plate, okay, and this is where you put the meat. Sorry, this is where you put the meat. Okay, so actually, if you think about it, there are three interactions that are happening now. There is the interaction between the plate and the meat. Okay, obviously the plate and the meat will have an interaction. So there's this interaction going on here. But there's also the interaction between the meat and the air. And there's an interaction between the plate and the air. Okay, so what is keeping this plate hot? Okay, or in a sense, what is keeping this plate hot is the air. Okay, it's absorbing the heat from the air to keep it hot. And at the same time, it is also being cooled down by the frozen meat. Okay, it is being cooled down by the frozen meat because the frozen meat is, interacting with the air and is releasing all this heat. Okay, sorry, it's absorbing all the heat from the air also. Okay, and so we find that there's heat being absorbed by the plate from the air and heat being absorbed by the meat, okay, from the air and from the plate. And of course, the meat, okay, is giving out, in a sense, okay, is giving out all the heat towards the meat. Okay, so what we don't want to happen is for the plate to cool down faster. So we want the plate to cool down as slow as possible, because the slower we can cool down the plate, okay, the easier it is for it to continue to defrost. That's why we need the specific heat capacity to be high. Okay, my first instinct, honestly, if you're speaking, my first instinct is the same as yours, probably. Okay, I would think that, oh, of course, I want the specific heat capacity to be low so that it will get hot faster. But don't forget, no, the opposite of get hot faster is not get cold slower, no, it's get cold faster. And that's exactly what we don't want. Okay, yes, it may take a long time to heat up, but once it is hot now, it takes a long time to cool down. And that one is more important, because if the plate cools down very fast, then the defrost plate is no longer a defrost plate, it is like a useless plate. Okay, so it will cool, down, okay, slower. Okay, it takes a longer time to cool down. Actually, the answer that I wrote here is it can absorb more heat without cooling down too fast. Okay, it is absorbing heat from the air to keep it hot, but at the same time, it is also losing heat to the meat. Okay, so we don't want it to cool down too fast, because it cools down too fast, then you absorb whatever heat from the air, so no point lah. Okay, so take some time. Okay, take some time to go through these 2 points. Okay, it's a bit weird lah. Okay, if you think about it. Okay, the color of the plate. Okay, the color of the plate. Sorry, hold on. Okay, the color of the plate is of course black lah. Okay, because black is a good heat absorber. Okay, it absorbs heat and light very well. Okay, the surface area of the plate is high. Okay, sorry, let me mark this first. So black, and so we have high. Okay, and why do we want to have a surface area of plate is high? So that it's able to absorb more heat, okay, from the surroundings. Okay, or it can contain more heat. Okay, so that it can defrost the meat better. Okay, then the arrangement of the plate. Okay, the arrangement of the plate is use 2 plates. Oh, sorry, you have 2 choices, right? Either use 2 plates, top and bottom, which is my choice, or use 1 plate. So use 2 plates, okay, top and bottom. Because the more plates you have, okay, then of course you get to store more heat lah. Okay, if I add another layer of plate over here, okay, if I add another layer of plate over here, then this plate now will get the heat from the air and from the next plate, so it's able to transfer the heat better lah. Okay, so the use 2 plates, top and bottom, to provide okay, to provide more heat for defrosting. Okay, and so the best plate will be defrost plate S. And then, as in the previous videos, remember that here needs to have 4 points. Okay, you need to write point 1, point 2, point 3, and of course, point 4. Okay, rewrite all the 4 points over here. Okay, to get that 10th and most important mark. Okay, now again, I just want to mention that probably the most difficult thing to digest is the specific heat capacity lah. Okay, and I think for me the main point is this lah. Yes, we want it to heat up faster, but this is defrosting, and when you're defrosting, you're losing heat. Okay, you're losing heat, and the last thing that you want is to lose heat too fast. That's why the specific heat capacity must be high, so that you can slowly lose heat without losing the temperature. Okay, the temperature remains high, although you're losing heat. It can store more heat, okay, without cooling down too fast. Okay, if you understand in that aspect, okay, then I think you'll probably be able to understand this question. Okay, the next question is question number 10. Diagram 10.1 shows the ballast vessels in a submarine. So you have the two ballast tanks over there. We have a submarine. So obviously when you have a submarine, the physics principle involved will be the Archimedes principle. Okay, Archimedes principle. Okay. Next question. Now 10.2, 10.3 shows a block of wood into liquids of different densities. Okay, so using 10.2 and 10.3, okay, we have to compare the volume of a block of wood that is immersed in liquid P and liquid Q. Okay, so let's compare the volume first. So obviously, since P is less inside, immersed, so obviously in terms of the volume, okay, P will be less than Q. Okay. Secondly, we have to compare the density of liquid P and liquid Q. Okay, compare the density of liquid P and liquid Q. Now, since P is a lot more afloat than Q, okay, so obviously P will be more dense than Q. Okay, because it is able to have a bigger buoyant force lah. Okay, that's why it's able to keep P afloat even more. Okay, third one is the weight of the block of wood. Okay, the weight of the block of wood will be the same because it is, sorry, okay, the weight will be the same. Okay, because it is a similar block of wood lah. Okay, identical wood. So since the wood is identical, so the weight must be the same. Okay, relate the volume of wood submerged with the density of the liquid. Okay, so since the volume of wood, since the volume and the density have different directions, okay, so obviously it will be inversely proportional, but you don't write inversely proportional. So the bigger the density, okay, the smaller. Okay, the smaller the volume of wood submerged. Okay, volume of wood submerged. Okay, the bigger the density, the smaller the volume of wood submerged. Okay, lastly, make a deduction regarding the relationship between buoyancy and the weight of an object. Okay, now this one is Archimedes principle. So Archimedes principle, when an object is floating, okay, when an object is floating, like in our case over here, so the buoyancy, okay, is equal to the weight of an object. Okay, that is floating lah. Okay. Of course, this is not talking about the weight of the water displaced, etc., etc. Okay, we're talking about just the weight of the object. When something is floating, the buoyant force is equals to the weight of the object. Okay, next question. Explain how a submarine can sink and float on the surface of the water. 4-mark question. So again, 2 marks for how it sinks, 2 marks for how it floats. Okay, so how does it sink? So water. So if you take a look, the ballast tanks, so what is where the ballast tanks come into play? Water is filled in the ballast tank. Okay, in the ballast tanks until the weight is bigger than the buoyant force. So the weight is bigger than buoyant force. Okay, causes the submarine to sink. Okay, basically it is a play on the weight. Okay, you want to make the weight bigger, you fill in the water, then it becomes bigger weight than the buoyant force. Especially if the whole submarine is already inside. The weight is so much bigger than the buoyant force, causing the submarine to sink. Okay, then of course, 2 marks for how it floats. Okay, so how do you float is you need to pump out the water lah. Okay, so this is a very normal question. If the submarine is already inside the water, how do you remove the water from the ballast tank? Because if you just open the hole, the water is not going to go out. Okay, so it has to be pumped out. Okay, so the water from ballast tank, okay, is pumped out. Okay, if you want to put, you can also put pumped out at high speed lah, because it is a very huge pump. Okay, it's pumped at high speed, and the point of this is to have the weight is smaller than the buoyant force. And when you have the weight smaller than the buoyant force, so causes the submarine to float. Okay, and that will be how the 4 points are distributed. 2 points for how it sinks, fill in the water, weight bigger than buoyant force. 2 points for how it floats. You pump out the water, okay, and then the weight is smaller than buoyant force, so the buoyant force is bigger, causing the submarine to float. Okay, diagram table 10 shows the characteristics of 4 structures of ship PQRS. Okay, different ships lah. So as a researcher in a ship manufacturing company, you are assigned to study the structure used to make the ship support heavy cargo, so heavy cargo ship. Okay, you're given 4 choices of structures, PQRS. The table above shows the ship structure. Sorry, shows the ship structure. Yeah. So explain the suitable characteristics, etc. Okay, this is a section B question, very normal. Okay, so obviously the shape will have to be streamlined. Okay, the streamlined shape will help you to navigate across the water more properly. Okay, the strength for the metal used. Sorry, this should be high lah. Okay, not wide nah. I'm just gonna assume that this is high. This is high, low. Okay, so I'm gonna assume the strength has to be high. Obviously, you don't want a low strength metal. Okay, the cross-section area, okay, has to be wide. Okay, you need a cross-sectional area of the ship base, okay, which means this way. Okay, the ship base has to be wide lah, because you want to support more cargo, you want to have a big ship lah. Okay, so and then after that, the volume of the airspace, okay, the volume of the airspace in the ship, okay, has to be high. It cannot be like very little airspace now. Okay, so obviously the best choice we have will be P lah. Okay, so let me write it down first. The shape of the ship is streamlined. Okay, the strength of the metal is high. The ship base cross-section area is wide. Okay, the volume of the airspace, the volume of the airspace is high, and the ship that we want is ship P. Okay, now we fill in the reason. So why do we want to have the streamlined shape? Is to reduce water resistance. Okay, as the ship travels, you don't want it to slow down because of the water resistance lah. Okay, so reduce water resistance. Strength of the metal used is high. Okay, you can say last longer. Okay, avoid rusting. Okay, doesn't break easily. All the standard answers lah. Okay, the ship base of the cross-sectional area is wide. Okay, and the reason for this is to increase the buoyant force. Okay, acting on the ship. Because a bigger cross-sectional area will mean that there's more water being displaced. More water displaced means you have a bigger buoyant force. Okay, and if you notice, this is the first one so far that has something to do with physics lah. Okay, talking about buoyant force specifically, yeah. Okay, the volume of airspace in the ship is high, also is for the same reason, okay, to increase the buoyant force, okay, acting on the ship. Okay, or if you want to talk about in terms of density, because if you remember the plasticine, if you have a ball of plasticine and if you change it into a bowl, the bowl will float because the density is less. Okay, you can also say decrease the ship's density. Okay, when you decrease the ship's density, then of course the buoyant force will be much higher lah. Okay, then again ship P, because the same 4 points again lah. Okay, make sure that all the 4 points are given over here, 1, 2, 3, 4. Okay, and remember never to use, because it fits all the characteristics above, as a definite answer that you cannot and must not use. Okay, let's carry on to question number 11, our final question. Finally, question 11. So this is a question from chapter light. So diagram 11.1, 11.2 show a light ray passing through the same glass block with different incident angles. So one is 42, and if you notice, it is going at this one, and one is at 48, and then it is totally reflected. So this is obviously something to do with total internal reflection. Okay, so what is meant by the critical angle? So in this case, the critical angle is at 42. Okay, 42. How do you know it's a critical angle? Because it is refracted 90 degrees to the normal. Okay, so so the critical angle is an incident angle. Okay, incident angle where the angle of refraction is 90 degrees. So the incident angle in this case is 42 and the angle of refraction is 90 degrees. Anything less than 42, okay, anything less than 42, it will be refracted lah. Okay, it will be refracted like this. But we see that the refraction is 90 degrees. So when the refraction is 90 degrees, that particular angle of incidence is called a critical angle. Okay, diagram 11.3 shows an incomplete light ray path entering a glass prism. The refractive index of the glass prism is 1.55. So calculate the critical angle. So the formula will be n equals to 1 over sine c. Okay, and then of course the this one is given 1.55 equals to 1 over sine c. Okay, so sine c equals to 1 over 1.55. You get this, and then you shift sign, you will get the answer c equals to 40.17 degrees. So the critical angle is 40.17 degrees, which means that if the incident angle is more than 40.17, then it will be totally internally reflected. Okay, so let's take a look at this. Copy diagram 11.3 and complete the ray path and state the incident angle. Okay, so in this case, let me change the color. Okay, in this case, the first thing we need to know is that after it enters here, because the plane over here is at 90 degrees, it's just going to enter. It's just going to enter over here. And then because this particular plane is sengit lah, okay, sengit in that sense, so we will need to draw a 90 degree normal line over here. Okay, and so the question now is because this is going from a more dense to less dense, less optically dense, the question now is it going to refract, or is it going to refract, which means it will go like this, or is it going to be 90 degree refraction, or is it going to be totally internally reflected? Okay, and so how do you know this? You have to determine what is this angle over here. This is the angle of incidence. Okay, now if you take a look at this particular triangle, okay, since this is 30 degrees, this is 90, so you know that this will be 60 degrees. And since this is 60 degrees, then you know that this is 30 degrees. Okay, now since this is 30 degrees, okay, and the angle, the critical angle, okay, is 40.17. So what do you think is going to happen? Is it going to be refracted? Is it going to be reflected? Okay, since the incident angle is smaller than the critical angle, it's going to be refracted. Okay, it's going to be refracted out lah. So the refraction outside will occur. Okay, it won't be totally internally reflected because the incident angle, 30 degrees, is smaller than our critical angle, which is 40.17. Just to remind you lah, okay, if the angle of incidence is more than the critical angle, it will be totally internally reflected. But if the the incident angle is ngam same as the critical angle, it's a 90-degree refraction. If the incident angle is less than the critical angle, it will be refracted. Okay, but this is in the case where it is going from more optically dense going towards a less optically dense region. So inside here, the glass is more optically dense. Outside here is air lah. Okay, air is less optically dense. Okay. Okay, let's continue. So diagram 11.4 shows an image of a coconut tree on the road that normally occurs when the weather is hot. This phenomenon is called a mirage. So explain how a mirage is formed. Okay, so you need the 4 points for this lah. Okay, so number one, you know what, I need to rub this off. Okay, number one, okay, on a hot day, okay, it has to be on a hot day lah. Okay, the air at higher levels, okay, the air at higher levels of the sky, okay, is cooler, okay, and more dense. Okay, so the light rays refract away from the normal line. Okay, I mean, because it's going from more to less, so it will refract away. So, and it will continue to do so. Okay, this continues. Okay, until the incident angle is more than the critical angle. And then when this happens, total internal reflection occurs. Okay, total internal reflection occurs. And so what we see, okay, so it will refract away until total internal reflection occurs. So when this happens, the image of the total internal reflection okay, is reflected towards the observer's eye. Okay, so what we see over here is the product of total internal reflection. Okay, so you see straight, if you draw a straight line over here, this is the image that we will see. Basically is, in order for total internal reflection to happen, the incident angle must be very big. And how do you get the incident angle to be very big? You need it to keep going further and further away from normal. Okay, so as it is being refracted by the layers of the air, is refracted away from the normal until the incident angle becomes big. Okay, and when it becomes bigger than the critical angle, it will be totally internally reflected. And that's how you see the image of the whatever it is that you are miraging, okay, in the observer's eye. Okay, final question. Diagram 11.5 shows an optical fiber that can be used in the fields of telecommunications and medicine. Okay, so you have the fiber optic over here. So as a researcher, you are assigned to investigate the characteristics of a specific type of glass used as the inner core of the optical fiber. Okay, state and explain your suggestions based on the type of material and refractive index. Okay, so sorry, not the type of material, the characteristics of the material. So you don't even have to mention the type of material. Okay, so this is a very general question, but it is one of the questions where you have to know. Okay, if you know fiber optics and you know the characteristics, you can actually it's quite easy to answer this. Okay, but of course, knowing this is the big challenge. Okay, of course, the most important thing is when you talk about the refractive index. Let's start with that. Okay, because that's only the only thing that we can have one. So the refractive index, okay, the refractive index of the inner core. Okay, so there are two cores in a fiber optic cable. Okay, in the fiber optic cable, there are two cores. One is the inner core and the outer core. The most important thing is this: the refractive index of the inner core, okay, must be bigger than the refractive index of the outer core. Okay, some books call it layer, some books call it core lah. Okay, doesn't matter. Yang penting, the inner layer must have a bigger refractive index than the outer layer. Okay, and this one, the reason is very simple. So more total internal reflection can occur. Okay. Okay, now that we've gotten that out of the way, okay, the refractive index is the only thing that actually you can mention. Okay, the rest all is actually quite factual. Okay, but if you cannot remember much, just remember these two has to come as a pair. The inner core or the inner layer refractive index must be bigger than the outer one because more total internal reflection can occur. And fiber optics is all about this. We want to have more total internal reflection so that you can have a stronger signal, you can have, your high-speed internet and your whatever it is okay, that you want for telecommunications and medicine. Okay, next, and these are standard answers. You need to have the material, okay, material with low density. Okay, I'm going to talk about low density first. So, of course, when you say low density, then the answer will be so that this one is light. Okay, another one is the material is strong material. Okay, so that it is long lasting. Okay, after a while, you see that these kind of answers it's like very standard one. Okay, if you put low density, sure, you talk about light. If you talk about strong, you should talk about long lasting, etc. etc. Okay, that is another one. Now, another one is the purity. And this is very specific. So the purity of the inner core material, okay, is bigger or is more than the outer core. The inner core material, the purity of the material, whatever you use, usually it's glass. The purity of the material must be much more pure. Okay, and this is so that more total internal reflection can occur, yes, but a better answer would be to avoid, okay, loss of signal. Okay, because all the signals are going in and going to be totally internally reflected. If it's not pure, then it's going to crash into another impure thing and it's going to mengacau lah. So we want the signal to be as clear as possible, okay, to be as line clear. Okay, another one is flexible material. Okay, because remember that optical fiber optics not just used in telecommunication, like high-speed internet, but also used to do like endoscopy. You put the camera inside the body without cutting it open. So you need the material to be flexible. Okay, if it is so strong and so hard, it's very hard to choose inside somebody's body So if it's very flexible, it's easy to go into whatever salodara or whatever, or into your to your usus, whatever it is in English. Okay, so it needs to be flexible. Okay, so that it is easy to bend. Okay, flexibility usually comes in easy to bend. Okay, and finally, and I think this is a very important aspect of fiber optics. You have many cables in a bundle. Okay, in a bundle. So you don't just have one piece of cable. You have many cables and you bundle it all up together. Okay, so then you say more signals can be sent. Okay, more signals can be sent and this is usually for telecommunication You want high-speed internet, you need more signals to be sent so that your internet can be faster. You can watch this video much easier. Imagine if our internet is just one single cable, one single piece of fiber optics, and once again, how slow would the internet be? Okay, so be very glad for technology these days. It allows me to record this and allows you to watch this recording at your own pace, at your own time, and according to whatever speed that you prefer. Okay, so that's it for our paper 2. I will see you all in the next lesson or the next video. I'm not sure which one. Okay, take care everyone and have a happy new year.